Let's get going.
Loosen up, bit of lunges, lunges. Action. There you go. Just do it. Just go with the flow of the lunges, Mark. Hello, we're back.
Yes, we decided as benefit to us we were going to go on to Unit 2 for a little bit before coming back to Unit 1.
Yeah, so when we first came to this house, it's then.
Not now.
Not now.
So that's why the sudden change from school hall hour-long videos to Jill's house.
And hopefully more segmented videos, more sensibly divided.
Yeah, because when we started we were just filming just for a little bit of fun. We weren't sure we were going to put them on YouTube.
No, we didn't really.
We just did hour-long videos.
Yeah, we just did everything. Because that worked? Well, it didn't. So we changed that.
Yep. So we're on Module 2 of Unit 1. This is part 1 of 3.
Yep. We are in the new academy now, so we could move in.
But it's really loud. There's lots of people.
There's loads of people.
And this is our board. We're not replacing
it. We're not. It's ours. I might call it Jerry.
I might call it Jerry. The academy isn't as bad as I thought. It's actually pretty good.
It's quite good, isn't it?
We actually each get our own card. That's how we
do
pay for
ID
things
cards.
now.
It's very, very FBI-like.
Yeah, but for copyright reasons, we can't show you that. So we edit.
Well, we made a few changes.
They look a bit like that.
A bit like that. So now you walk into a room, we do this. Yes.
And when we pay, we do this. And yeah, you use your card for everything. It's quite exciting, but we're not moving this in there, so we're staying at Jill's house.
Yep. So now onto the proper bit.
Yeah.
Chemistry.
So the start of Module 2 of Unit 1 says evidence for shells.
But what are shells?
Well, shells are where the electrons are kept. You're familiar with from GCSE. Shell 1 has 2 electrons, Shell 2 has 8, and so on, as you're familiar with.
Yeah.
But it was quite hard to prove that for many years.
Yeah, but they thought they were there, but they couldn't think of a way of proving them. And then they thought, let's fire off electrons and see what happens.
Yeah. That's called ionisation energy.
Yeah, that's called ionisation, but it requires energy.
Yeah.
And the amount of energy it requires helps us prove evidence for shells. There's quite a few factors about ionisation energy, and well, what are they, Wim?
Well, firstly is electron shielding. You've got your inner shell, then the next shell, and just say you're in the next shell as well, and you're knocking an electron off the third shell, if you like. You're going to knock it off, make a positive ion. The different layers repel each other, so there'll be less pull to the centre on the outer electrons if there's more shells.
If there's more shells, so if there's one electron in the outer shell, like in potassium.
Yeah, potassium works.
And then you remove that. It'll be less shielding.
Yeah, it'll be on the next shell for the next ionisation.
So it'd be quite a lot harder to remove the electron because they're all much closer to the middle.
And that's called electron shielding, and that's the definition you need to know, much like ionisation energy.
So, learn your definitions.
Electron shielding.
There's another one. That's repulsion.
Yeah.
It's also to do about the electrons repelling each other. Because they're all negative, they don't like being near each other, so the more you have, the further they spread.
Nuclear charge.
That's to do with the amount of protons. That's the nuclear bit, and it's the positive pull that brings all the electrons in, which just increases the ionisation energy, whereas E2 decreases.
Yeah. And so there's any more electron. Oh yeah, the G. Electron shielding. Repulsion. Nuclear charge. Atomic attraction, or nuclear attraction. Nuclear attraction increases as you get closer, but it's often a different marking point to the electron shielding, despite being all to do with the same thing.
Yeah.
If they're close to the nucleus, there's more nuclear attraction because of less shielding, but they're two separate marking points.
Yeah. And how does this actually prove for shells then, Wayne?
Well, if you have, we could do a graph like this of energy up the side against the number of ionisation energy. So the first one will be knocking off one electron, then you knock off another, and so on. So 1, 2, 3, 4, 5. And let's say we use something in group 3, so aluminium, for example.
Yeah.
This is all to do with Al. The first ionisation energy will take X amount of energy.
Yeah. But because this is when the electron is furthest away from the nucleus, it'd be quite easy to remove relatively.
Yes. Now there isn't much change in electron shielding because it's in the same shell, but there is a little bit because there's only 2 that pulled a bit closer, so it increases a little bit, and a little bit more.
Then this is where the proof comes from.
Yes. After it's lost 3 electrons, it will then be in the shell before, which is neon. No, it's not neon. Chlorine, argon. Which one is it? I can't remember.
One, same as one of the noble gases.
Yeah. So that's a new shell,
Yeah.
and it's got the full octet, but that's much less of this electron shielding.
Yeah. So it flies up. These are experimental values, and it was explained using what Wayne said.
And then it will go up.
And then
like
it'll go
that.
up, and every shell it does, it will fly up a lot. And these are diagrams you need to know.
This flying up proves the evidence for shells. There you go.
Yeah.
That's that.
Pretty swish.
You also would be expected to be able to write an equation or
Yeah.
something.
For ionisation of something. I don't need a definition, I'm not going to go through, but it mentions gaseous atoms.
Yes, so you have to put for one of your marking points if you have to write it gaseous.
Yeah.
So let's use the example of lithium, it's the one that's in the book.
Okay. So
Start
we
off
have
with
1 mole of gaseous lithium atoms, and
Just
we
need a definition.
and we ionise it,
Yep.
fire an electron off it. It becomes positively charged because electrons are giving it the negative charge. You take one away, positive, and then we have an electron just chilling.
That doesn't have its states because we don't know what state an electron is.
No, it's just sort of
But these
Different.
have to be gaseous for an extra mark
yeah.
because of this definition. So learn that and learn that. That often comes up.
It is.
The repulsion. And that's pretty much ionisation energy.
It is.
So let's move on with the cause.
All right, let's crack on. We're back.
With shells and orbitals.
Absolutely. Who else has a shell, Wayne?
A friend of ours. Hello man, I'm Fabio Avogadro. I have a shell, look. I'm a descendant of Avogadro himself. Ask me anything about moles. They're my favourite dish. See you later, guys.
So, shells.
Yes. Firstly, a little reminder from GCSE, how many electrons are in each shell? And how do you work it out if you've forgotten?
Yeah, well, there's a pattern.
Yeah.
In the first shell is 2.
Yeah. Because n would be 1. 1 squared is 1 times 2 is 2.
Yep.
Second one, 2 squared is 4 times 2 is 8.
Yep.
9 times 2 is 18, and 16 times 2 is 32. You only have to bother about the first 4 shells with this pattern.
It's true.
So that's how you work it out, but you should remember 2, 8, and then you'd be able to count them if you wanted to.
We'll work it out after that. But shells are made up of things.
Yes, the idea you had at GCSE that electrons are like little planets whizzing around, it isn't quite right.
No, they say they're sort of teaching in the beginning, but really they're just lying. We don't know what an electron is when it's
no
orbiting.
idea, there's lots of theories about what an
No.
electron could be and its properties, but...
So we know the region it is sometimes. We call that an orbital. This sort of follows a sort of orbit pattern, and there's a few patterns you have to know.
Yes. Firstly, every orbital can hold up to 2 electrons.
Yeah.
So first we have s orbitals.
You do.
S.
That's the first one, and these ones sort of are like a disc on a plane.
Yeah.
It sort of looks a bit like that.
And every orbital of that will contain 2 electrons.
And you're right there, sort of like this. So one electron goes up, the other one will be repelled with the other way.
Yes, they have to have opposite spins in the exam.
Yeah.
And that's that.
Yeah.
Then we have, so this can hold up to 2 electrons, and each orbital can hold up to 2 electrons. Then we have p orbitals, which is where it starts to get slightly more confusing.
Yeah, they're not a disc on a plane. They're like dumbbells.
Yeah, it's sort of like 3 discs, because of the repulsion, they sort of stretch out a bit.
Yeah. So one's sort of like that.
then one sort of goes across
There's
it.
one that goes across in the middle.
And
There's
then
another
one
one
comes
that
out in
comes
3
out.
dimensions.
Yeah,
It's hard to draw.
I'll draw it this way and just sort of. Yeah.
So this one can hold 2 electrons, and every orbital can hold 2. This one can hold 6 electrons, so it's got 3 orbitals.
Yeah.
So that's 3 of these boxes. And if it's a full, you've got to have every one with opposite spins.
You go on how to fill those in
Yeah, I'll go on
a
to
bit
it.
later.
You then have D and F orbitals. These are different. I'm writing them together.
Yeah, because you don't need to know what they look like. They're a bit more complicated.
Yeah.
We need to know really.
You need to know that D can hold up to 10 electrons, so would have 5 of these orbitals.
Yep.
With each one holding 2.
And you need to know what part of the periodic table they relate to, because these all relate to part of it.
Yes, and that's actually the next page in the book, so let's go on to that.
Alright.
All about subshells.
Orbitals around 2.
Yep. So, to do with subshells and the actual naming of orbitals, how they fill up.
Yeah.
Yep, here.
So, yeah, periodic table, much like when you get in the exam.
So we're going to annotate it in terms of subshells.
Yeah, we mentioned before that each subshell sort of occupies an area periodic table. I'm going to show you where it are.
So this is the top, the hydrogen and the neon.
Yep.
That's S, they're both S.
Yeah.
They can hold up to 2 electrons, so it couldn't be a P, so it has to be an S. Here we have 2S, 3S, 4S.
This section is different. It's P.
Yes, if you
Because
look
there
up,
are 6 along here.
Yeah.
Makes sense.
so this would be 2P, 3P,
So it would be
4P.
boron, carbon, nitrogen, oxygen, boron, fluorine,
So
and
that's
neon.
helium, not neon. I named it wrong, but.
Yeah.
And then this is 3D. This is better explained when we go through examples.
It is. So, should we do that?
Yep, what example do you want to do?
Well, first thing I'd like to do one that involves D shells.
Yeah, naming as much as you can.
Yeah.
F shells are actually down here. If you look on your periodic table, it's got like dots here. And
Yeah, and
dots down here.
actinides and
Lithiumide, something like that.
yeah, something like that. And they're bonkers sort of man-made things, and they do weird things because they're not really stable. You don't
Yeah.
need to know about that yet.
You don't need to know about that. You might be asked to appreciate that this is the F.
Yeah.
It is in your syllabus, but I doubt it very highly.
Yeah.
So let's do a D, shall we?
Yeah.
What
Should
would
we do iron?
Okay, Fe.
So write out what you need to do. It fills up all the ones up to, and halfway through that.
So Fe is actually the 6th one
It is.
along here. You have it like that in your periodic table.
So we start off at the start. Makes sense.
1s2 is the first of the S's. The 2 indicates that both the electrons fill it up. 2s2 because it's full. 2p6 that can hold 6 and it's full. 3s2 is full. 3p6 is full. 4s2 comes before the 3d because you're going from left to right when you read, and that's full. 3d only goes to 6 because this is the 6th along, indicating there's only 6 electrons in the orbitals.
Yeah.
There is a shortcut. You can do,
You can use noble gases.
yes, so the noble gas before its row, which is in this case,
Argon.
so you put it in square brackets like that, you go argon.
And that will show all the way up to 3p6.
Yep, 3p6, that just shows you're starting at this point instead of starting at 0.
So you just need to say
The rest.
4s2 and 3d6. That's a lot quicker.
Yes,
But
but
you're not always allowed to do that.
yeah, unfortunately in the exam they often start by putting fill in the rest, and they put 1s2, 2s2, then you've got to do the rest.
You got to do the rest.
So you can't do 1s2, 2s2,
Argon. Yeah,
It doesn't make sense.
Doesn't make any sense. It's crazy. Yeah. Also, filling in orbitals changes a bit sometimes.
For example, if you have ions,
Yeah.
what
So
ion should we use?
we could use an ion of iron, or we could use an ion of aluminium or something.
Yeah, we'll do aluminium so that's easier. That makes
Right.
it 3 plus ion. So, should we start with aluminium as an atom?
Okay.
Aluminium is here.
It's the first 3p one.
So, by our
Like
naming
before.
methods, you want to do it?
Yeah. It fills up all before.
1s2's full, 2s2's full. 2p6 is full, 3s2 is full, 3p only has the 1, so that's how that one goes. Then you have its ion,
Yeah.
3+.
And you know from before, Al makes a 3+ ion.
That means it's lost 3 electrons.
Yeah.
So it goes back 1, 2, 3. It will now be up here in terms of subshell.
Yeah. And it would be the same as neon.
Neon. 1s2, 2s2, 2p6.
Yeah.
And that's how you do ions. You have to appreciate what's happened to the electrons and where the new subshell is.
Yeah. I think we should do another example. Sometimes the orbitals fill up in a special order, and you can't really tell that some of the examples we've done here. So if we do sulfur,
yeah,
which is
sulfur's sort of here.
It is.
After sulfur, you've got chlorine, then the noble gas. So it is literally here. You've got S.
Yeah. So if we draw that up like we've done here.
Okay. So S. 1s2 is full. 2s2 is full. 2p6 is full. 3s2 is full. Then it's 3p4. Right. That's that in terms of subshell. Now let's do it in terms of orbitals. So the drawing thing we did before, I'll do it in red.
Okay. So when you do orbitals, you throw in sort of levels of energy.
Yeah, and the levels of energy increase as you go up.
They do.
So that's your 1s2. Your 2s2 is exactly the same, just a little bit more energy.
You call these energy levels. Makes sense.
2p6 is a bit higher, but it's a p, so it's like this.
Yeah, it's got 3 orbitals, but 6 electrons. Again, you need to remember the opposing spins.
Yep, that's a mark.
There you have 3s2, and then you have 3p4. That's where it gets a bit interesting. Orbitals have to fill up in a special order.
Yes.
They have to do all the first ones first. How?
Because they all repel each other.
Yeah, so each orbital repels each other, so once that goes in there, that will repel, so it wants to go into the next one, then that will repel, then it will go into the next one, and then it fills in normally, so the next one would be in the first one there.
So a mark would be lost if you were to do something like that.
Yeah, that is not right.
Because that would repel and push it into that one, because there's space.
Yeah.
So that's something to mention, yeah, that's orbitals and how to fill them up. This should be revision. So
This should be revision,
don't do
so
any more than that, but
yeah.
that clears it up.
Alright.
Next we introduce chemical bonding. So,
Ooh.
let's do it.
An introduction to chemical bonding.
Yeah, we'll actually go on to it more in part 2, so this is just an intro. Why do things bond, Triv?
Well, that's a good question. Things bond because they have unpaired electrons. So take something like carbon, that has 4 electrons, that is one there, one there, one there, and one there in its outer shell. These all want a pair.
Yeah.
They want to complete their octet.
So that can bond with many things to make its 8 outer shell electrons.
Either 4 hydrogens or whatever.
Yep, and basically everything that isn't a noble gas has the unpaired electrons. That's what forms bonds.
Yeah.
Noble gases, well, they have their full octet. They're stable without reacting.
So they don't react.
And we have some uses for that. But
first,
let's go through the different types of bonding that things that don't have a full octet can do.
Okay.
Because it's not all the same for everything.
It's not.
Despite doing similar things, they're slightly different in their own way.
Yeah, so we start with something like carbon dioxide.
Yeah, okay. CO2.
So
It's drawn like that because it has 2 double bonds.
it does.
These bonds are covalent.
They are because both of these are gases.
So
There's covalent bonding. Then if we have something like
sodium chloride, salt.
yeah,
Typical example. NaCl. This is ionic
Yeah.
bonding.
because these are ions. They're not gases. One's a gas, one isn't.
And then
And
something
finally-
like copper.
Yeah, copper and magnesium.
Cu is just.
That's metallic bonding because it's just a metal.
So essentially, if something from that side bond to something with this side, it's ionic.
Yeah.
If these two things bond together, like oxygen and stuff like that, it's
Covalent.
covalent.
And these one
All
things.
things in the middle, and if this side bonds to this side, That's metallic.
It's metallic. Yep.
But we go through that in part 2. So
We do.
next we have the uses of the noble gases, because it is quite useful if
Yeah,
they don't
if they don't react.
So-
They all have uses they prefer you to know though, because they are all just quite good insulators and stuff.
Yeah.
But they have others. So we start from the top.
Okay, first we have helium. You're familiar with it, raising balloons at parties
Yeah.
and stuff.
Yeah, it raises really big things like airships.
Airships, that's
yeah,
the use they
that's
want
the
you to
use. They don't want to know that it makes Jimmy sound really high pitched.
know. They don't care
They
about
don't care
that.
about
That's
Jimmy.
not really a use. It's just a thing that's totes funny. Then we have neon. What's that used for, Triv?
Well, the neon lights, it's used for big billboards and flashy things in Las Vegas.
Yep, all the big signposts that say "come this way to this." They're all neon in
They're
there.
all neon.
Argon is used in filament light bulbs.
Like one you can't see right there.
Yeah, this one you can't see. It's really cool.
Yep, it's beautiful. I've never seen something quite like it, to be honest.
Anyway, argon's used in that. Then we have krypton.
We do, and
That's used in laser eye surgery.
yes, not just with night stuff to kill Superman.
And finally, because radon is also a noble gas, but we don't have much of that. It's barely on Earth at all.
Yeah,
Xenon. That's used in car headlights.
it is. Show you where you're going. Isn't that nice? But yeah, this is the end of part 1.
Yep, we'll see you at part 2. We're going to sum up this
Right at the
part,
end.
part 2 and part 3 at the end.
Yeah.
So we're not going to do a summary now.
No.
So roll the credits.